Section: Introduction. In this section, we will discuss how pre-trained large language models, LLMs, have shown impressive performance on various benchmarks and datasets that previously needed specialized neural network architectures. While LLMs excel on general benchmarks with custom instructions or in-context examples, they may not work well for all real-world applications. LLMs have limits on the amount of input they can handle, which can restrict the number of examples or instructions we can provide to guide their behavior. For simple tasks aligned with the LLM's pre-training data, extensive prompting may not be needed. However, using LLMs in specialized domains like specific medical fields or private data can be challenging. It may require long prompts for good performance, increasing latency and cost. Moreover, LLMs may forget or overlook information in long contexts, affecting accuracy. Although retrieval augmented generation (RAG) addresses some challenges, it can retrieve irrelevant information, impacting generation performance. Fine-tuning, especially with parameter-efficient fine-tuning (PEFT), has reduced the computational resources needed. But successful fine-tuning requires sufficient training data, which can be scarce and costly to obtain. To tackle the issue of limited training data augmentation methods like synonym replacement and back translation are commonly used. However, these methods may not effectively expand the dataset for fine-tuning LLMs in new tasks. Recent studies have explored using LLMs to augment the dataset, proving more effective. Yet, indiscriminate augmentation without considering the LLM's accuracy on individual data points can be suboptimal. To address these challenges, we introduce LLM2LLM, a targeted and iterative data augmentation framework using a teacher LLM to expand the training dataset efficiently. Our approach involves fine-tuning a student LLM, identifying incorrect predictions, and augmenting those data points iteratively. We evaluate LLM2LLM on various datasets and observe significant improvements in model performance. Furthermore, we conduct ablation studies comparing LLM2LLM with existing methods and variants to validate our design choices. We find that the targeted and iterative nature of LLM2LLM is crucial for enhancing model performance. In the background and related work, early studies focused on fine-tuning instructions using NLP datasets, while Self-Instruct introduced a self-bootstrapping framework. Subsequent work leveraged stronger models to enhance general-purpose instruction following models. Section Summary. In this section, we introduce LLM2LLM, a targeted and iterative data augmentation framework that efficiently expands small task-specific datasets by fine-tuning a student LLM on the initial dataset, identifying incorrect model predictions, and using a self-instruct style data augmentation to improve accuracy. When benchmarked on various datasets like GSM-8K, Casehold, SNPs, TREC, and SST2, LLM2LLM shows significant performance improvements ranging from 24.2% to 52.6%. Ablation studies confirm the importance of the iterative and targeted approach in enhancing model performance compared to existing baselines. Section: Self-improving LLMs. In this section, we explore using self-improvement techniques to fine-tune language models, LLMs. Previous methods involved filtering the model's outputs and fine-tuning based on those outputs. Our approach, LLM2LLM, differs by not directly fine-tuning on its own outputs. Instead, we use a teacher model to provide feedback through synthetic data. Other recent works also aim to enhance LLMs iteratively, combining ideas from reinforcement learning and self-play. However, LLM2LLM stands out by focusing on task-specific fine-tuning in low-data scenarios, unlike others aiming for stronger general-purpose LLMs. Our method uses only the incorrect data points during training, and the teacher model augments these points with synthetic data, simplifying the training process. Data augmentation has long been studied in natural language processing, NLP, with methods like easy data augmentation, EDA, augmenting data at the character and word levels. Recently, There is a trend to use LLMs to generate new training data, such as August GPT using ChatGPT to rephrase text for data augmentation. While these techniques create large amounts of synthetic data, it has been found that fine-tuning on smaller subsets can yield similar results. Our methodology assumes an LLM model pre-trained on a source dataset and aims to adapt it to a new domain using a small seed dataset with potentially unseen characteristics. We focus on enriching the target dataset with an LLM to improve performance. We propose a general LLM-based data augmentation pipeline that iteratively generates new training data based on the student model's performance. This approach differs from knowledge distillation, as it can improve performance even when the teacher model lacks domain-specific knowledge. Our framework aims to enhance the student model's performance by generating conceptually aligned data points based on the teacher model's feedback. Section Summary. In this section, we introduce a novel approach called LLM2LLM, which focuses on fine-tuning language models, LLMs, in a low data regime using a teacher model to provide feedback through synthetic data, unlike traditional methods that directly fine-tune on model outputs. We also discuss the importance of data augmentation in NLP, highlighting approaches like August GPT that leverage LLMs to generate synthetic data efficiently, and propose a general formulation for an LLM-based data augmentation pipeline to address limitations in indiscriminate data augmentation strategies. Section: LLM2LLM. In this section, we present the end-to-end algorithm of LLM2LLM in our paper. We were inspired by self-instruct and utilized the teacher model M_text teacher to generate synthetic data for the data points where the student model struggled during training. To explain further, we initially trained the baseline student model M_text student on the target data D_0 and assessed its performance. We then identified the incorrect training examples that the student model found challenging, E_I. The teacher model was then used to create additional training data points that were conceptually similar but semantically different to these incorrect examples. It is important for the teacher model to have reasoning capability to follow the data augmentation instruction and generate data points akin to the incorrect examples. There are some key design decisions in LLM2LLM. Notably, we only prompt the model with examples from the seed data during augmentation, unlike LLM2LLM. This decision helps prevent data degradation from multiple augmentation iterations and limits the amount of new data being generated. By restricting the input wrong answers during dataset generation to only data from the original seed data, we can control the total number of training data points. Our empirical evaluations support this approach. To evaluate the effectiveness of LLM2LLM, we fine-tuned Llama 2-7B on various target datasets such as GSM-8K, Casehold, SNPs, TREC, and SST2. We experimented with different sampling rates to assess performance across various low data scenarios. We also used different teacher models like GPT 3.5, GPT-4 Turbo, Llama 2-70B, and Ouroboros L2-70B. Additional experiments were conducted to ensure that the augmented data from the teacher models differed from the test dataset used for final model evaluation, addressing potential test data leakage issues. We discussed the performance of LLM2LLM with varying amounts of training data, focusing on fine-tuning Llama 2-7B on GSM-8K using GPT 3.5 as the teacher model. The results show significant accuracy improvements, especially in low data regimes. LLM2LLM consistently enhances model performance across different datasets. We illustrate the improvement in baseline accuracy on GSM-8K and Casehold with each iteration of applying LLM2LLM, showing substantial accuracy gains, particularly in scenarios with limited training data. Section Summary. In this section, we present the end-to-end algorithm of LLM2LLM, which leverages a teacher model to generate synthetic data from incorrect training examples to enhance the student model's performance. We filter and prompt the teacher model to create additional training data aligned with incorrect examples, focusing on maintaining dataset quality and preventing data degradation. Through experiments on various datasets, including GSM-8K and Casehold, we demonstrate that LLM2LLM significantly boosts model accuracy in low data regimes by iteratively generating additional examples based on model mistakes, showcasing its effectiveness in improving model performance. Section: Comparison with other augmentation methods. In this section, we compare our method with other augmentation techniques like IDA and AugustGPT. We also check the performance when adding more data from the unseen training set. Our method, LLM2LLM, outperforms naive fine-tuning by more than 20% on GSM-8K and by around 35% on Casehold. It also outperforms IDA and AugustGPT by significant margins on both datasets. The key to these improvements, especially compared to AugustGPT, lies in LLM2LLM's ability to generate targeted examples based on the model's weaknesses, unlike AugustGPT, which augments data without focus. This targeted approach allows for more efficient use of the augmented data budget. We have mainly showcased LLM2LLM's performance with GPT 3.5 as the teacher model, but other large language models, LLMs, can also serve this role effectively. A stronger teacher model is expected to produce higher quality augmentation and, consequently, higher accuracy. When we tested LLM2LLM with different teacher models like GPT-4 Turbo, Llama 2-70B, and Ouroboros L2-70B on GSM-8K, we found that the accuracy varied significantly. For instance, with 74 seed data examples, LLM2LLM achieved 11.8% accuracy with Llama 2-70B, 15.0% with Ouroboros, and 19.8% with GPT-4 Turbo. This aligns with our expectations, as GPT-4 Turbo is known for its superior mathematical reasoning compared to other models. We also conducted ablation studies to justify the design choices in LLM2LLM. One important aspect we evaluated was iterative augmentation versus one-shot augmentation. Our results show that iteratively augmenting data over multiple steps outperforms adding all augmented data at once. This iterative approach generates one data point per incorrectly answered example, leading to better performance on datasets like GSM-8K and Casehold. Furthermore, we explored the impact of data augmentation using only seed data versus using both seed and previously augmented data. Our findings indicate that evaluating and augmenting data solely from the seed dataset yields better results compared to including previously augmented data. This is because using augmented data for further augmentation can deviate from the original data distribution, affecting performance. Lastly, we compared from scratch fine-tuning with continuous fine-tuning in LLM2LLM. From scratch fine-tuning consistently outperformed continuous fine-tuning, showing up to a 9% improvement in accuracy. Continuous fine-tuning may lead to overfitting on small seed data over multiple iterations, especially in scenarios with limited seed data. Restarting fine-tuning from scratch in each iteration with augmented data helps mitigate this issue and improves overall performance.